Welcome to you all to this MOOCs online video course, Theory of Yarn Structure. In the last 3 lectures, we were discussing about mass irregularity of yarns. Though we majorly spoke about slivers, however, the basic concepts of Martinelli theory as well as bundle theory are also valid for yarns. So, the same expressions we can use for mass irregularity of yarns also. Now, we will discuss about some numerical problems based on what we learned so far in this module. So, we start with our first numerical problem 1. So, consider a sliver which is prepared from cotton fibers of 25 millimeter mean length and 0.16 tex mean fineness. The counts in kilotex of the sliver measured at 5 different places are 5.9, 5.5, 5.7, 5.6 and 5.8. Determine the coefficient of variation of number of fibers in the cross section of this sliver. Coefficient of variation of number of fibers in the cross section of this sliver. So, if you study module 5, then you will realize at one point of time we have derived that coefficient of variation of fiber number is equal to under Poisson distribution this. So, we need to basically find out n bar and then square root. So, what are the data given? Capital T in kilotex 5.9, 5.5, 5.7, 5.6, 5.8, and we need to see fiber fineness is also given 0.16, same for all 5 readings. Then we need to find out number, small t, right, into 1000. So, 5.9 kilotex means 5900 tex divided by 0.16. This will give you this number. Then 5500 divided by 0.16 will give you this. Then 5700 divided by 0.16 will give you then 5600 divided by 0.16 will give you a very nice number 35,000. The last one 5800 divided by 0.16 will give you this. So, 5 readings of number we can find out average this will be equal to 35625. So, this is the average number of fibers present in the cross section of the sliver. Then V n is equal to 1 by square root of this will give you 8. So, this is the answer. If you wish to express it in terms of percentage, then 0.5298 percentage. So, the coefficient of variation of number of fibers in the cross section of sliver is equal to 0.5298%. So, this was your numerical problem 1 and solution. Now, we proceed to numerical problem 2. So, this is your numerical problem 2. Calculate the coefficient of variation of count of cotton sliver of 0.10 any mean count. So, .905 kilotex and mean fiber fineness is given, tex. Coefficient of variation of fineness of fiber is also given in terms of dimensionless, it is 0.35. Now, you are asked to calculate the coefficient of variation of count of cotton sliver. So, Martindale's formula. So, this formula, if you substitute the data, it will give you the required value. Right. So, this will lead to dimensionless. If you wish to express in terms of percentage, five. Right. So, this is the required answer. The coefficient of variation of count of sliver is 0.55 percentage. Now, we will go to problem number 3. The coefficient of variation of count of cotton slivers is often expressed as CV limit is equal to 106 root over n bar. This expression is often found in textile literature. While deriving this relation, how much is the coefficient of variation of fineness of cotton fiber considered? So, you are asked to calculate coefficient of variation of fineness of cotton fiber, if this is the expression for coefficient of variation of count of cotton sliver. So, we rewrite this expression in our symbols. V t is equal to dimensionless given, right. The formula used to calculate this was this. So, if we equate, we have to find out V small t. So, square so 0.3516. So, you see that this particular expression is valid for cotton sliver, and when coefficient of variation of fiber fineness is 35.16 percentage. But often we think that this expression is valid for all cotton fibers, irrespective of the variety of cotton fibers used to produce those fibers, which is not correct. So, this expression is true if this is the CV of fiber fineness. If the CV of fiber fineness changes, of course, this value will not be 106, instead of 106 it can be some other value. However, there is a tendency amongst us to use this expression for all cotton slivers or all cotton yarns, which is not correct. So, you have to first find out, in reality, in practice, you have to first find out the coefficient of variation of fiber fineness, then you have to use Martindale's expression, then you have to find out CV limit. Similarly, there is another problem associated with wool fiber. Based on that, problem number 4 is designed. The coefficient of variation of count of woolen slivers or woolen yarn also is often expressed as CV limit 112 root over n bar. In case of yarn, it will be yarn cross section, right. Then you are asked to find out the fineness of wool fiber. So, we rewrite this expression using our symbols. Right. Right. Square, which is equal to 2544. Then zero point 5044. So, Also we have observed that this expression is frequently used for all woolen sliver, which is not correct, because this expression is valid only when wool fiber has a mass CV of around 50%. If this number changes, then this number will change. So, what we have to do in practice when you need to find out the limit CV of woolen sliver or woolen yarn, you have to first find out the fineness of CV of fineness of wool fiber, then you have to use Martinelli's formula, then you have to find out the correct quantity here, right. In this way you need to do in reality. Now, we come to problem number 5. It is a quite long problem. Consider that a drawframe is fed with 6 cotton carded slivers of the following specifications. Sliver number 1, mean fiber fineness 0.15 ktex, CV of fiber fineness 35% and mean sliver fineness is 5.9 ktex. Second sliver is different from first one, mean fiber fineness 0.16 ktex, CV of fiber fineness 35.16% and mean sliver fineness 5.91 ktex. Third sliver is different from 1 and 2, mean fiber fineness 0.20 ktex, CV of fiber fineness 34.10% and mean sliver fineness 5.95 ktex. Similarly, all other slivers are different. So, these 6 different slivers are fed in a drawframe and as a result we double it, we obtained one sliver, double sliver. You need to find out the CV of count of the double sliver. Right. So, how do you find out this problem? So, let us solve this problem. What we have to do is that we have to find out the variance of the double sliver, mean of the double sliver and from there CV. But before that we have to use Martinelli's formula to find out the CV of individual slivers, is not it. So, let us do that. Now, sliver number, this was given, this was given, this was given 1, 2, 3, 4, 5, 6. Sorry. So, we have to first find out this mean dimensionless using Martindale's formula. What is Martindale's formula? Right. So, using this formula, T bar is given 0.15, capital T bar is given 5.9 kilotex, you have to convert it into tex, that is multiplied by 1000, and V t is given in percentage. So, dimension is it will be 0.35 square plus 1. So, this value you will obtain as 53. Let me write it in terms of unit. This is dimensionless, this is in tex given, and this is kilotex given. So, you have to multiply it by 1000, then V square T in percentage given. So, it is square quantity, right, after square plus 1. So, the first reading I will tell you 0.15 divided by 5.90 into 1000 into 35 square divided by 10,000 plus 1, this will lead to 0.0053. Similarly, for the next one roughly same reading 0061, then you will get 0058, then you will get 0063, the last one you will get this. So, this is the individual you will get. Then you have to find out the variance. So, from this table you will find out the variance. Precisely now, how to find out variance? Square. So, for the first one, square of 0.0053 into 5.90 square. So, its unit will be kilotex square. So, this reading you will see you will get this value. For the second sliver 0.0053 square multiplied by 5.91 square, this will give you little different. For the third one 0.0061 square multiplied by 5.95 square, you will get this value. For the fourth one 0.0058 square multiplied by 5.93 square, which will lead to for the fifth one 0.0063 square into 5.98 square, for the sixth, the last one, 0.0057 square into 5.93 square, this. Then what you have to do? You have to basically sum all this. So, if you sum up all these readings, all these 6 readings, what you will get is 70.21 into 10 to the power minus 4 kilotex square, and also you have to sum the mean sliver fineness, this will give you 35.6 kilotex. So, you know variance, you know mean, you will be able to find out CV. How you will find out CV? Let us go to next page. So, double sliver by this. So, this is your 70.21 into 10 to the power minus 4 and T bar is your 35.6. Okay. So, you will see this will probably come this. So, 0.0024. So, in terms of percentage, if you wish to write, .24. What is interesting, you see, not a single individual sliver has less than 0.0024. So, all individual slivers had a higher mass irregularity, because of doubling the CV becomes 0.0024, which is why doubling is carried out, right. So, this was the solution of problem number 5. Now, we proceed to problem number 6. Consider that a draw frame is fed with 8 cotton carded slivers. Each carded sliver has 4 kilotex mean count and 6% coefficient of variation of count. So, what is given here is 4 kilotex and is given, doubling is 8. Okay. So, what will be the variance of individual one? This. What will be the unit? Kilotex square, right, and what will be the summation of all variance? Is basically which is equal to 0. Square. And what is the fineness of double sliver? ktex. So, you know variance, you know mean, you have to find out CV. This will give you 0.0212. If you wish to express in terms of percentage, .12%. So, the coefficient of variation of count of the double sliver is 2.12%. So, this was your problem number 6. Now, we proceed to problem number 7. A cotton sliver of 5.9 ktex mean count is prepared from fibers of 25 millimeter length, 0.16 tex mean fineness and 35% CV of fiber fineness. So, let us see what is given. This is given tex, this is also given, assuming all fibers are inclined at an angle of 5 degree from the axis of the sliver. Calculate the coefficient of variation of count of the sliver. So, you remember the theory, when theory of CV of sliver fineness, when all fibers are inclined at the same angle from the axis of the sliver. We derive this relation V t is equal to small t bar by capital T bar cos theta V square t plus 1. This theory we have derived. So, if we substitute, capital T bar is also given tex. So, if we substitute, capital T bar 0.16 5900 cos 5 degree 0.35 square plus 1. This you will see value will come approximately equal to 0.0055. So, if you wish to express in terms of percentage, .55. This problem seems to be very similar to problem number 2, except the fact that the angle is 5 degree. In problem number 2, angle is 0 degree. We found this value. When the angle is 5 degree, we found the value remains same. Instead of 5 degree, if this value would have been say a little higher, 15 degree, 20 degree, then this value would have been higher. As the angle is very small, near to 0, so its impact on the mass CV of the sliver is not seen. However, if the angle will be higher, then this value will be higher, which will be different from 0.55. Right. So, problem number 7 is completed. Now, we proceed to problem number 8. This is problem number 8. A cotton sliver of 5.9 ktex mean count is prepared from fibers of 25 millimeter mean length, 0.16 ktex mean fineness and 35% coefficient of variation of fineness. This sliver exhibits Worcester CV of 4%. Determine the index of irregularity of this sliver, comment on the results obtained. So, this is your problem number 8. Let us see what is given. So, capital T bar is given, ktex, small t bar we will require, ktex, V t is given and actual is given. You have to find out index of irregularity. All right. Index of irregularity, actual by limit in terms of our symbol by limit. So, this value is given, this value is not given. So, we have to find out this value using Martindale's model. Right. This is given 0.16, this is given 5900, this value is given squared, this value is given. So, this will be equal to, we have already solved this problem, 0.0055. So, if we substitute 0.04 divided by 0055, which will be equal to 7.27. It should have been near to 1 if Martindale's theory was correct, but it is becoming 7.27, too high index of irregularity. That is the comment. Right. Let us apply Bornet's theory, and we would like to find out this value using Bornet's expression and also index of irregularity using Bornet's expression, and we would like to see if using Bornet's empirical correction index of irregularity will be less than this or what. So, let us continue. Bornet's empirical correction. So, what was Bornet 1 by 2 T bar by capital T bar 1 by 3 T plus 1 to the power half. This was the expression given by Bornet. So, we use the data given in the problem, T bar 0.16 and 5.9 ktex. So, 5900 tex and 0.35 plus 1 to the power half. So, this value you will get 0.0165. See, limit irregularity is greater than 0.0055. This came from Martindale. Right. Now, index of irregularity V effective by Bornet. So, this value was 0.04 0165. So, what will be this value? 2.42. And what was the value using Martindale? 7.27. So, index of irregularity is remarkably less, we found using Bornet's theory, 2.42, and here it is 7.27, right. So, this was the solution of problem number 8. Now, we proceed to problem number 9. Problem number 9. A yarn of 29.5 ktex mean count is prepared from fibers of 0.17 ktex mean fineness and 18% coefficient of variation of fineness. So, what is given here is capital T bar 29.5 ktex, small t bar 0. This and V t 0.18, and also actual measurement measured CV of yarn is given. As I told you earlier, all the expressions what we found for sliver, they are also valid for yarn. So, in practice Martindale's formula, Bornet's formula, bundle theory formula are applied in case of yarns also. So, we will use those formulas for yarn as well. Okay. And two parameters are given, A for from this and B from this. These parameters are obtained from Worcester statistics data. These two parameters were obtained based on Worcester statistics data. So, here actually we have to compare these three theories, Martindale's model, Bornet's empirical correction and Nesker's model. So, these three theories what we have learned so far will be compared in this numerical problem. So, let us do that one by one. First, let us find out Martindale. Martindale's formula, as we know, right. So, fiber fineness is 0.17 ktex and yarn fineness 29.5 ktex and your CV was 0.18 plus 1. Okay. So, this will lead to 0.771. Then index of irregularity using Martindale, .45, significantly higher than 1. Okay. Now, let us use Bornet's expression. Bornet's VBT, B stands for Bornet, M stands for Martindale. This was not half T bar by this to the power 1 by 3 into B square T plus 1, that was Bornet's, right. So, half, what is T bar? 0.17 and this 29.3 to the power 1 by 3 squared plus 1. So, this will lead to 0.0927. Then index of irregularity using Bornet, V effective by V Bornet, that is equal to 0.189 divided by 0.927, which is equal to 2.04. This value is little less than this value. So, the Bornet's idea of clusters forming sliver is probably correct. Now, we have to use Neskers model, bundle theory. Show what was this bundle theory data. So, let us write V n t. You remember t bar by this A plus B, that was the formula. Show what is t bar given, this by this, and what is the value of A given, 1.36 plus B is 0.028 into 29.5 by 0.17, right. So, this will lead to 0.1893, and then index of irregularity using Neskers theory by this. So, 0.189, 0.1893. Close to 1. Right. So, if we compare this idea or model and index of irregularity I and dimensionless, Martindale, Bonnet's idea and Neskers model. So, Martindale, it was 2.45, this was 2.04 and this was 4. So, what we see is that this index of irregularity is least in case of Neskers bundle theory and highest in case of Martindale's theory. So, probably this Neskers theory is quite well. So, problem number 9 is over. Now, we proceed to the last problem, problem number 10. Determine the mean number of lower units in the higher units in problem number 9. So, it is a continuation of problem number 9. So, let us see what is given. This was given and also A and B given. Right. Now, we use Poissonian sliver. So, first we find out this value from the given data. This is basically 173.53. So, this is our one value. Right. Second, as it is Poisson distribution, then we remember this becomes equal to this. So, by q for 1 and this value is equal to 0.028. So, this leads to the value of 4228 into 173.53, which will be is equal to 4.86. We get the second reading. Right. Then we will find out the third one by using this formula. Into Q21, right. So, Q21 will be equal to 41 by 42. 41 is 173.53 and 42 is 4.86, right. So, this value will be equal to 35.71. Okay. Then we use this expression A is equal to 1 plus V square T plus Q 43. Now, A is given, A is your 1.36, 1 V square T is also given in this problem. .18 plus Q 43. This will lead to Q 43 is equal to 1.36 minus this and this. So, 0.3276. So, we get the another fourth reading. Okay. Then we use this expression Q 43, Q 32, Q 21, then Q 32 will be equal to 41 divided by 4321. Now, what is 41? 41 is we have calculated 41 is 173.53 divided by 43 we have calculated 0.3276 and 21 also we have calculated 35.71. So, this ratio will give you 14.83. So, this is our another unit we found. Okay. Then we use another expression Q 31 is equal to Q 32 Q 21. Then Q 32 is 14.83 and Q 21 is 35.71. 529.58, so large number. At first sight this seems to be improbable. However, there could be many bundles that are empty. Look at the value of Q43. Q43 is 0.3276, is very less value. So, that means, in the sliver there are huge number of bundles, but the number of fibers in the bundle is very less. So, there are very few fibers, there could be possibility that many bundles are empty, that is why you get so large reading. So, now if we summarize all readings we have, 41 is 173 point this, 42 we have 4.86, 43 we have 32 this, then we come to 32 we have 14.83, 31 we have 529.58, and also we have 21 we have calculated this. So, this is the mean number of lower units in the higher units. This is the answer to the problem. This ends numerical problem 10, and also this ends module number 5. Thank you very much. Thank you for your attention.